Very good morning to one and all. So today I would like to share my thought and the work which I carried out at ARCI regarding hydrogen fuel cell as an alternative energy solutions for electric vehicles. So basically, I don't want to go into deep about our institution because my previous colleague Dr. Ganesh has shared about ARCI. It's autonomous R&D institutions. Comes under Department of Science and Technology. So we have a headquartered at Hyderabad, and we have two centers functioning at IIT Research Park, Chennai. So the one from Center for Fuel Cell Technology, where I'm coming from, and another is Center for Automotive Energy Materials. So I mean, the main motto of ARCI is that it's not only a R&D institutions. So the work which we carried out and technology which we developed has to be translated to the industry for the end user. So that is the uniqueness of ARCI when compared with other research R&D institutions in this country. So far, I think we have transferred about 16 technology to 28 industries for the various applications. I mean, we are also offering JRF, SRF positions every year, depending upon the number of positions which are available. So depending on the project actually. So we used to have our own way of selections, conducting interviews and written examinations. If you qualify those steps, you can register your PhD in any of the NITs and IITs in India. So we have a MOU with almost all the IITs and NITs, and we can do. We will support them for 5 years with the full fellowships until their completion of the PhD. So that is one message which I want to convey to the participants, and we have very good infrastructures in terms of characterizations and executions of and scaling up of the process. So coming to our center, it's a Center for Fuel Cell Technology. It's established in 2004, and we have about 20,000 square feet, and we are located at the second floor of the IIT Research Park. It's a multi-story building. So it's about 20,000 square feet, and we have a quite number of employees ranging from senior scientists to scientists and research fellows and technical staffs and students and trainees. As I said earlier, the mandate of the center is that to cater the technological needs of the existing or upcoming industry. So eventually there is a commercialization which we are working towards that directions. And main objective is that we need to develop a hydrogen-based PM fuel cell system. It's not only a PMFC stack, it's an entire system. So if you talk about the system, then we need to consider about all the balance of plant which are required to make a viable system for the power generations application, especially for stationary as well as transport application. So that is our major objective of our centers, and we are working towards that directions. So as you are aware that we are looking for alternative energy sources, so moving from fossil fuel to hydrogens. So I mean, all of a sudden we cannot switch over from fossil fuel to the need hydrogen based energy economy. So there is a kind of intermediate stage currently which we are crossing, I feel, that is electric vehicle based sectors. So that will be the intermediate stage, and the ultimate objective is that environmentally friendly and carbon free or carbonless hydrogen-based vehicles for power generations, especially for the transport and stationary applications. So that would be the ultimate objective of the entire world, looking to move from fossil fuel-based energy to the hydrogen-based energy system. And so that there are many energy storage systems and systems are available. So why do we need to go with hydrogen energy? The answer for that question is that it's simple, because it's high energy density when compared with any of the fuels. So it has about 142 megajoule per kg of hydrogen. So that is quite high when compared with all other fuels. So it can be, and as I said, it is not existing as such. So we need to generate from hydrocarbon or from water. So ultimately that can be carried out using renewable energy as a source to get the hydrogen from the fossil fuel or water-based system. And when you use this in fuel cell, there won't be any carbon containing problems. There won't be any carbon emissions when you use through fuel cells actually. That is, these are the driving force for the global community to move towards hydrogen economy. And when you use it for fuel cell vehicles, as I said, the emissions of carbon is zero almost. So these are the driving force for us to think about and move towards the directions for hydrogen-based economy, especially for the transport and stationary applications. Before going into the hydrogen fuel cells, I mean application of the hydrogen fuel cells for the electric vehicles and stationary application, just I would like to give a just a basic about fuel cells, so that I hope most of them you are aware of that functioning of fuel cells. So it's a hydrogen is a fuel, so it takes hydrogen in and puts electricity and water vapor out actually. So when you do these combustions in terms of indirect combustions, is electrochemically way of converting hydrogen into power. So the hydrogen get oxidized at the anode. It's a basically electrochemical system. So you need to have anode and cathode. So which are all based on platinum-based catalyst, carbon-supported platinum-based catalyst on both sides. So when you pass this hydrogen gas to the anode compartment, it gets split on the surface of the platinum and generate proton and electrons. So that electron goes to the external circuit, and when it reaches the cathode surface where the oxygen or air which are available, so get reduced into water. So the ultimate product which we get is power and water. So that is the uniqueness of this technology. There is no carbon emissions, and there is no other greenhouse gases emissions during this process. And so basically it's the electrochemical system. So which so in any electrochemical system, we need to have electrodes which are anode and cathode, and you must have an electrolyte. So depending upon the electrolyte which we are using for the fuel cell, these fuel cell can be categorized into 5 to 6 different types. Apart from the electrolyte based, which can also be categorized based on the operating conditions, because the temperature which is playing a major role. So depending upon the operating temperature and type of electrolyte which we are using in fuel cell, it can be categorized as a solid oxide fuel cell and molten carbonate fuel cell and phosphoric acid fuel cell, alkaline fuel cell, and proton exchange membrane fuel cell, where we can use hydrogen or low carbon alcohols, aliphatic, can be used as a fuel. So that is named as a direct methanol fuel cell or direct ethanol fuel cell. Ultimately, that ethanol will act as a source for hydrogen, which will generate instinctively in the anode compartment. So that also comes under the proton exchange membrane category. So these two, among these fuel cell, these proton exchange membrane fuel cell gaining lot of momentum for the stationary as well as the transport applications, because of the operating temperature is very low, near ambient conditions. And the solid oxide fuel cell, also getting momentum, especially for the stationary applications, because the operating temperature is quite high, so which we cannot be used to for the transport applications actually. So the onboard based system, the solid oxide fuel cell may not be suitable, since because of the operating high temperature, so which we need to have a very good thermal management system, which is not possible for the onboard applications. So it's meant only for the stationary applications. So when you come for the transport application, the only choice is the proton exchange membrane based fuel cell, where you can operate the system is near ambient conditions, and it will be very compact, and I mean it is very compact, and it can be easily integrated with the motors, electric motors which are available in the vehicles actually. So that is the driving force to use this proton exchange membrane based fuel cell for the stationary as well as the transport application. In all these fuel cells, hydrogen is the fuel, so which is getting oxidized at the anode compartment, and air is the oxygen, where it gets reduced at the cathode compartment, ultimately to form a water as a byproduct, along with power generations. So depending on the applications area, this PM fuel cell, as I said, it's also be used as a consumer electronics, especially for the ethanol based fuel cells, And SOFC, as I said, it's only for large scale generators, especially for the stationary application. And these molten carbonate and phosphoric acid fuel cells are a high temperature and medium temperature fuel cells, which are also going to be used for small, large scale stationary application. But because of the carbonate formations and all those issues, these fuel cells will not take it up further for the commercial uses. And DMFC, it's only meant for the consumer electronics like a mobile, laptop, and cameras. I mean, so it's a low power density fuel cell, so it cannot be used for the transport or stationary application higher capacity. So it meant only for the consumer electronics like mobile and laptops actually. So just get to know about the PEM fuel cells. So it's basically the any fuel cell, especially the polymer electrode membrane fuel cells, the open circuit potential for the fuel cell is about 1.23. That is a theoretical, but in the practical case, we will get only about 1 volt actually. So, so that is the open circuit potential for the PEM based system. When you talk about the polymer electrode membrane, so the main component in this fuel cell is the polymer electrode membrane, which will act as a separator as well as the electrolyte. So that is the, and this electrode. So the electrocatalyst, which is act as anode and cathode, has been coated on the two sides of the membrane. So once if you coat this catalyst on the membrane, you will get a membrane electrode assembly, which is the heart of the PEM fuel cells actually. So in both sides, people are using the carbon supported platinum as an electrocatalyst. So the amount of loading which we are applying on anode and cathode side will vary, especially the large resistance and large overpotentials in terms of electrochemicals, which are occurring only at the cathode side. So in order to overcome that issues, the high platinum loading, which is usually applied on the cathode side than the anode side. So this membrane electrode assembly is the core component for the PEM fuel cell stack. And apart from this membrane electrode assembly, you need to facilitate two gases. One is anode, I mean fuel cell, hydrogen gas has to be circulated at the anode compartment, and air which has to be pumped at the cathode compartment. In order to facilitate this gas transport within the fuel cell system, fuel cell stack, you need to have a proper flow channel. So in order to facilitate the gas transport, so that is called the bipolar plate. Basically, it's a graphite based things which will have channels. So and it has an inlet and outlet. So to facilitate the gas transport at both sides. So this graphite based plate is being used as a flow fluid plate for both hydrogen and oxygen side. And in order to, so once if you assemble this membrane electrode assembly and gas flow fluid channel, I mean flow fluid plate, you need to have a N structure, rigid structure that is called the N plate. So which will form a PEM fuel cell, actually single cell. So as I said, each cell will produce 1 volt, but once the moment if you draw the current, the voltage will come down like battery. So depending upon the voltage requirement and current requirement, the number of cell is being added in parallel or series connections actually. So if you see this, the theoretical voltage, though it is 1.23, once moment you will get about 1 volt. So that is 0.2 to 0.3 volt loss is due to the activation losses, which is very common in all electrochemical system. That is also common in fuel cells. So we are losing about 0.2 to 0.3 volt in the open circuit potential. And depending, so once the moment you draw the current, the voltage will drop down. So depending upon the fuel cell efficiency is being determined depending on the operating potential of the system. So depending on the operating potential of the system. So say for example, you are getting 1 volt and you are trying to operate at the cell at 0.6 or 0.5 volt, the efficiency of the system will be about 60 to 50%. So 50 to 60%.
Excuse me, sir. Sir, a request from a participant. He asks to press the hide button in the screen sharing tab because it hides something from the slide.
Okay.
Yes.
Yeah.
Yes.
Now is it okay?
Yes, sir. Yeah, yes, sir. Thank you, sir.
Okay. Yeah. So depending upon the operating voltage, the fuel cell efficiency can be determined based on the open circuit potential. So as I said, if you operate the system at 0.5 or 0.6 volt, the efficiency of the system, it's about 50 to 60%. So the fuel cell is an energy conversion device. Ultimately, the efficiency of the system is higher when compared with all the energy conversion device. If the chemical energy is converted to electrical energy. So not only electrical energy, it also liberates some thermal energy. So if you see on whole aspect, when you compare with the electrical and thermal efficiency, the conversion efficiency is about 60%, sorry, 80%. So the in this 80%, 50% will be the electrical energy output and 50% will be the thermal energy output. So if you operate the 1 kilowatt PM fuel cell, you will get 1 kilowatt electrical power. Apart from that, 1 kilowatt heat. So thermal energy you will also will get it. But only thing is that is low grade heat, which cannot be used for various application other than room heating and water heating purpose. So on the whole, if you see that conversion efficiency is 80% in terms of energy efficiency, but in terms of electrical efficiency, it's about 40 to 50%, and remaining 40 to 50% is the thermal efficiency. So that is the information, this IV curve which is representing here. And the main component of the PMFC is the membrane it's a naphion, it's a proton exchange membrane. It's basically a Teflon backbone which is being functionalized with the ether linkage and the active SO3H sulfonic acid group, which is responsible for the proton transport. So it's basically a very transparent thin and membrane, so which will act as a separator for the gases as well as the proton to transport from proton from anode compartment to cathode compartment. So as I said, the platinum electrocatalyst is being used. So in order to apply that platinum catalyst, we need to have some kind of substrate. So that is gas diffusion layer. So which is mostly carbon cloth or carbon paper, which are widely used. So this catalyst has to be coated on the gas diffusion layer. And once if you coated this electrocatalyst on the gas diffusion layer, that has to be transferred to the membrane by hot pressing. So you have to apply some pressure and temperature in order to bind this gas diffusion catalyst coated gas diffusion layer to the membrane. So that will form a membrane electrode assembly, which is the core component for the fuel cell. So you have a MEA, as I said, this is a flow field plate, which is most important to facilitate the gas transport on both sides. And if you have all those components, you will form a single cell and with the end plate and tie rods in order to pack the anode and cathode very compactly. So this is the typical representation of the single PM fuel cell. And as I said, which we are handling gas and it also producing a water. So we need to have three different phases. The electrodes are solid and the reactant are gases and the products are liquid. So we need to have a proper water management and thermal management within the system, because the water is producing at the cathode compartment, but at the same time you have to allow the gases effectively to reach the catalyst surface in order to favor the electrochemical reaction. So we have to be very careful in removing the water management, removing the water which is produced within the cell. So this gas diffusion, and we need to, but at the same time, the diffusivity of the gases to the electrocatalyst surface has to be uniform. So this gas diffusion layer should have a electrical conductivity, and it should have a porous in nature, and it should have a mechanical strength, and it should have a heat conductivity. So these are the main function and properties of the gas diffusion layer. So all these factors, the gas, I mean the carbon cloth or carbon paper, which is meet all the requirement of this fuel cell. So this is the typical carbon cloth and carbon paper microstructure, and it has to be processed, it has to be treated hydrophilic and hydrophobic. So it should not be so hydrophilic and it should not be so hydrophobic. So it should be kind of optimum. So because you need to have a proper electrical conductivity. If you increase the hydrophobicity of this carbon cloth or carbon paper, you will lose the electrical conductivity. But at the same time, if it is so hydrophilic, so the produced water within the system will get choked within this fuel cell. So it has to be hydrophobic also. So we need to optimize the hydrophobicity and hydrophilicity of the gas diffusion layer. Accordingly, we need to do some kind of treatment in order to facilitate this gas transport as well as the water removal. So that is the role of the gas diffusion layer and its function. Coming to the electrocatalyst, so platinum is a very good electrocatalyst in terms of hydrogen oxidation as well as oxygen reductions. But due to the cost volatility and the cost, considering the cost, so we need to try to minimize the platinum content on both sides of the fuel cell. So in order to reduce the platinum content and make it more conductive, and in order to utilize effectively for each and every particle of the platinum, so the carbon is being introduced, or carbon is being used as a support medium to facilitate the electrochemical reaction at both the compartment. So this carbon will, because the platinum nanoparticles, as many of the lectures you might have heard in the past few days, so these platinum nanoparticles are highly active. So in order to avoid the agglomerations, the role of carbon is also playing a major role when you use the platinum nanoparticles. And this carbon supported catalyst is being used as an electrocatalyst for the fuel cell. And the main ultimate aim is to use low platinum content on both sides of the electrodes. And next is that membrane, which is most important, and this only component is making the whole world is a monopoly. The Dubon is the Nafion membrane is the monopoly in this technology, and there are many R&D program going on all over the world, but none of them can meet these required properties, and none of them meet these properties of Nafion. So many of the world, and almost 60 to 70% of the world community is depending on this membrane if you want to make a PEM fuel cell stack. So the uniqueness of this membrane is that it will facilitate the transport of photon from one compartment to another compartment, and it also absorbs water. So hydrophilicity, and because it has a tendency to absorb water molecule. So if you want to carry out the proton transport within the membrane matrix, it should be in wet conditions. Then only the effective transport of proton conductivity of the membrane will be high. So the membrane should be in wetted condition. So it has a tendency to absorb water. But at the same time, if you operate the system at a very high humid conditions, so the water logging is taking place within the system. As I said, we need to be optimum in maintaining the water within the fuel cell system, fuel cell stack. And the limitation of this, because the 25%, more than 25% of the cost, it goes to membrane cost. Because if you develop a 1 kilowatt fuel cell stack and say for example 3 to 4 lakhs rupees per kilowatt, so about more than 25% of the cost goes to this component. So and it has a very good mechanical strength. So it's basically a thin membrane. So if it get peeled off or it get pores, so the direct combination of hydrogen and oxygen will lead to explosion. So that kind of mechanical strength should also be there. So it meets that requirement. It has a very good mechanical strength in terms of assembly, and it is highly pore free, and it will not allow the mixing of gases inside the cell, and it has a very good proton conductivity, and it has a very good thermal stability as well as the mechanical stability. And if you form a membrane electrode assembly, so in any electrochemical system, if you try to minimize the inter-electrode distance between anode and cathode, so obviously you can reduce the resistance of the cell. So here in the case of PEM-based technology, the inter-electrode distance depends on the membrane thickness. So there are various kind of membrane thickness are available in the market. So 117, 115, these are the various configuration of the membrane. The last digit 752 represents the mil. So that represents the thickness of the membrane. Say for example, Nafion 117. So 7 mil, so 1 mil is equal to about 25 micron. So 7 into 25 is 175 micron. That is the thickness of the membrane. So that is the distance between the anode and cathode. So if you try to minimize the interelectrode distance by using very thinner membrane like 212, only 50 micron is the thickness of the membrane, which will determine the interelectrode distance between anode and cathode. So if you use the thinner membrane, the resistance of the cell will come down. So the performance will go up. So that is the kind of trade-off which we need to consider when you assemble a PM fuel cell system. And as I said, the catalyst loading at anode side should be low because higher exchange density, higher kinetics nature of the hydrogen oxidations. And in terms of oxygen reduction, especially, so it is a very slow kinetics. So in order to increase the kinetics, and we need to use higher platinum content. So the cathode have a more platinum content than anode. This is a bipolar plate, which I discussed earlier. The graphite plate is being widely used as the bipolar plate, and it has a very good electrical conductivity and thermal conductivity and mechanical stability. So all these factors, desirable features, which is having. So most of the PM fuel cell stack is being fabricated using graphite as a flow field plate, which will facilitate the gas transport on both sides of the cell. And as I said, the stoichiometric quantity of hydrogen and oxygen has to be varied depending on the load which we are drawing from the system. So obviously, you need to say, for example, H2 plus R42 will give H2O. So for example, you are handling about 1 kilowatt system. So you have to pass 12 liters per minute of hydrogen and 6 liters per minute of oxygen. So it should be in the stoichiometric ratio of 1:0.5 ratio. So in order to handle such kind of volume of gases at the two different compartment, we need to have two different flow field channels. So which will determine the volume of gas which we need to occupy at a particular time in order to draw maximum amount of load or current from the system. So there are various kind of design patterns are available. So depending upon the type of application which you are using for the fuel cell, so it can be varied from grid type or straight parallel, a single serpentine, multiple serpentine. So which are all different flow patterns of the gas molecules in order to handle the stoichiometric hydrogen and oxygen. And ultimately, this is also one of the cost component in the PM fuel cell. Here also it's about more than 25% of the fuel cell stack cost goes to bipolar plate, and which will also determine the volume of the fuel cell stack. Because as I said, if you want to increase the current, or if you want to increase the current, you have to increase the electrode area. If you want to increase the voltage, you have to add number of cells more. So so if you increase the more number of cells, you need to put more number of bipolar plate. So which will determine the volume of the PMFC stack. So as long as if you use very thin plate, graphite plate, so the volume of the fuel cell stack will come down. So this is also a deciding factors in terms of volume occupancy of the fuel cell, especially for the transport and stationary applications. So once if you form all the components, you can make a cell, and depending on the current and voltage requirement, the multiple of this unit will form a PM fuel cell stack. These are the schematic single and PM fuel cell stack of a hydrogen-based system. And as I said, the water management is a very crucial steps in PM fuel cell, because if you remove all the water from the system, the membrane conductivity will go down, because the proton conductivity will be effective only in terms of when you have a water within the system. So, but at the same time, if you keep more water within the system, which will not facilitate the gas transport taking place from outer side to inner side, and which will not allow the gas enter into the catalyst surface. So the water management is a very critical steps in PM fuel cell stack. So it should be hydrophilic as well as hydrophobic. It's the kind of optimum condition which we need to attain in terms of making membrane electrode assembly. And the water management is a very crucial. It should be kind of optimum way within the system. And as I said, the thermal management, it's also crucial, because 1 kilowatt system will also produce 1 kilowatt heat, but there is low grade heat. So we need to effectively because the operating temperature of a PM fuel cell stack is about 60 to 70. So if you operate more than that, actually the membrane dehydration will take place, because if you operate the system more than 100 degrees Celsius, the water vapor will go out actually. So the membrane dryness will occur. So that create a proton conduction loss that reflects in the performance. So the optimum temperature for the PM fuel cell stack is about 50 to 70 degrees Celsius. So in order to maintain that temperature, you have to effectively remove the heat which is produced during electrochemical reaction. In 1 kilowatt system, as I said, it's about 1 kilowatt heat has to be dissipated. So we have to have a proper thermal management. So water or air as the coolant, which is widely used for the PM fuel cell stack. But the water-based cooling system is viable when you operate the system in higher kilowatt. So up to 3 kilowatt, you can use air as the coolant. But when you develop a stack more than 3 kilowatt or 5 kilowatt, you need to go with a water-based cooling system. So you need to give attention in selection of thermal management, the cooling system, because that comes under parasitic loss, because you need to operate a cooling system, so that should consume less power. And there is a thumb rule: when you develop a 1 kilowatt PMFC system, the parasitic loss, especially for the thermal management and water management and fuel and oxygen supply system, all these system subsystem power requirement should be less than 10% of the main power productions. So when you create such a kind of a PMFC system, say for example you are creating 1 kilowatt PMFC system, and this thermal management system itself consume more than 500 watts of power, then there is no meaning for using that thermal management system for this fuel cell application, because you are using 50% of the power generated for the cooling purpose. So when you are selection of that thermal management system, you need to be very careful in terms of power consumption or in terms of volume occupancy within the system. So the thermal management is playing a major role, and the effective heat removal has to be effective heat distribution has to be carried out within the fuel cell stack. So as I said, so when you talk about the PMFC fuel cell stack, it's a stack. So when you talk about the system, we need to consider the hydrogen as a fuel. So the hydrogen which is not existing as such, so it has to be produced from hydrocarbon or water. So you need to have a fuel, maybe hydrocarbon, natural gas. So that is a fuel. So you have to process that hydrocarbon especially for methane. So that has to be converted into hydrogen rich gas. So methane has to be converted into hydrogen. So that is called fuel processor. So reformations, you have to reforming the natural gas into hydrogen. So fuel is a methane. So that has to be reformed into hydrogen using fuel processor. So the power, fuel cell stack, that is a power section, and you need to have a air supply system. So depending upon the load, depending upon the current which you are drawing from this fuel cell, you need to pass hydrogen and air accordingly. So load following gas flow controller. So 1 kilowatt system, you can operate at 300 watts also. So that time the fuel consumption and air supply has to be minimum. So same 1 kilowatt system, if you operate at 700 watts, you have to increase the flow of hydrogen and air. So depending upon the load following gas flow controllers are most important in your making PMF system component, and that is a power sections. So here we have a fuel, and it produces heat and water as a byproduct, and you will get a DC power. So it's a battery. So it's also producing a DC power. But when you compare with battery, the difference is that battery will produce high voltage and low current, but fuel cell will produce low voltage and high current. Okay, so the entire power electronics is different when compared with battery. So batteries are low current and high voltage, whereas fuel cells are high current and low voltage. So you need to handle the current, higher current. So obviously the power electronics has to be remodified, has to be restructured, and has to be restudied if you want to make a Pakka power conditioner for the fuel cell. So though it is a producer DC power like battery, but the outputs are different. So you need to have the commercially available inverters which are meant for the battery may not be suitable for the fuel cell. So in developing country like India, we don't have a such kind of optional product actually. So the power conditioner, so which we need to create our own, and the power electronics playing a major role, and that aspects converting the DC power into AC power. So and the fuel cell is a variable voltage. So the battery, if you say lithium battery or whatever it is, the voltage window for the is very limited. Whereas in the case of fuel cell, the open circuit potential is 1, but the operating potential is 0.6. So you have a 10 cells which is giving you open circuit voltage of 10. Once the moment you draw, you have to operate the system at 6 volt. So the difference between 10 and 6 is high, which are not in battery. So the operating voltage and the obtained voltage window is very low in terms of battery, whereas in the fuel, in the case of it's a variable voltage. So you need to have a proper DC-DC converters or inverters has to be built if you want to get a constant DC power from the fuel cell. That has to be converted again into AC. So during that time, we need to consider the selection of proper power conditioner, which is whatever the commercially available power conditioner may not be suitable for the fuel cells actually. So that is, so when you talk about all those components, it's a PM, it's from a PM system, PM fuel cell system component actually. So and the control and monitoring system is also a major component in PMFC system, because each cell, so you have a 20 cell stacks. So each you have to monitor the health of the each individual single cell, because some cell may have a 0.6. Say for example, 10 you have a 10 cells stack. So if you each cell will produce 1 volt, so you have a 10 volt, and if you operate at 0.6 volt, the overall stack voltage will be 6 volt. So in that case, you have to monitor the each and individual cells health actually. So whether all the cells are giving a 0.6 volt, or sometimes some cell may be 0.3, some may give 0.8. So but the average will be 0.5 to 0.6. But if you fail to monitor the each and individual health of a single cell, it will get collapse the entire system. So the control and monitoring of the system is also playing a major role when you develop a PMFC system. So and the control strategy. So we need to have some kind of strategic way of controlling these parameters, and especially in the case of fuel cell, all the it's a current driven process, because it's not a voltage driven control strategies. These are current driven, basically a load. Okay, so if you have a 1 kilowatt system and operating at 500 watts, so the amount of water production will be low, the amount of heat production will be low, and the amount of fuel consumption will be low, and the diffusion process will be low. But if you operate the same system from 1 kilowatt, all these parameters are changing. Heat productions will be more, water generation will be more, fuel consumption will be more, and diffusion process of the reactant will be more. So all these processes are controlled by the current. So we need to have a control strategy. We need to develop an algorithm. It's a current driven and complex physiochemical system in the case of fuel cell, not voltage based things. So when you develop a control and monitoring system for the PMFCG, everything is based on the current driven process. That's what I want to highlight here. And so just I would like to when you talk about the PM system, these are the factors which we need to consider. So considering all these factors, the major activities which are taking place in our center is that it's not only a PMFC stack development, we develop a entire system which we have discussed in previous slides. In some of my previous slides, we take care of all the subcomponent, power consumption and functioning and compactness, volume, and all these considerations we are considering when you make a PM fuel cell system. And as I said, we also have a hydrogen generation program in a bigger way, and we developed a system about 2,500 liters per hour production capacity. And we have some kind of spin-off technologies because if you see the supercapacitors and next generation batteries, these are all spin-off technology of the fuel cell, because most of the components are similar to PM fuel cell, and most of the material which we develop is also used for other spin-off technology like supercapacitors and batteries. So this is our fuel cell development, and we also do a lot of R&D on materials development and component development for the PMFC. But if you want to make a system level, you have to start with the commercially available material. So if you want to make a system level, let's say for example 5 kilowatt, 10 kilowatt and 20 kilowatt systems, we will buy the commercially available components like catalyst and membrane and bipolar plate, and we do membrane electrode assembly, and we do stacks, and we build the stacks, and we will develop our own control system and BOP components, and we will demonstrate the system for the stationary transport application. That is one activities. Parallelly, we also develop a material which is being tested initially in single cell level. If it works fine, we will take it up for the next level of short stack and full stack. So that is our parallel activities, R&D activities, which are also going on with the help of the students and other scientists. So we do parallel activities. One is system development, other is the component development, and other is the material development. So we try to cover all aspects of this technology. So ultimately, the cost reduction is the objective. So we try to minimize the cost and we try to reduce the cost of the system, as well as increase the durability and reliability of the system. So this is our PMFC technology development. As I said, one of the core component is the bipolar plate, and ARCI has the technology to, we try to replace the natural graphite, which are widely used for the PM fuel cell stack fabrications. So ARCI has a technology of exfoliated graphite, which are 50% lower density than the graphite, so which will always reduce the stack weight. So we use that exfoliated graphite material for making our own bipolar plates, so which are very compact, and the machining of, if you want to make a grooves, the machining is it's a tedious process, especially for the graphite. Whereas in the case of exfoliated graphite, you can create a flow channels on the exfoliated graphite by simply molding technology. So that is the uniqueness of our PM fuel cell stack. So this is 50% weight reductions in the overall stack development, and it can also facilitate the process of creating a flow channel over over graphite flow field plate. And weight reduction, we could able to achieve 50% than the graphite. That is the uniqueness of our PM fuel cell stack. And we have demonstrated ranging from 1 kilowatt to 20 kilowatt for the stationary applications. So it's a completely grid independent. So if you have a hydrogen cylinders, so you will get the power. So we have a small battery in all the system in order to initial startup for all the components, BOP components. So for example, blower, you have to supply air. So you have to activate the mass flow controller for the hydrogen supply, and you have to power on the converters and inverters. So all these functions, the initial power requirement is being met out by the batteries. So in all the systems have small battery for the startup power, and once the system is ready to function, so the battery is also being charged with the fuel cell. So we have demonstrated the fuel cell stack ranging from 1 to 20 kilowatt for the stationary application, and we have almost so the fuel cell will produce a DC power that has to be converted into AC. We have a single phase, and up to 5 kilowatt we have a single phase. More than 5 kilowatt we have a 3-phase system, so which was demonstrated within our premises. And as I said, fuel cell produce a DC power, again you need to convert it into AC. So we try to avoid that step, because again the conversion loss will be there, so that will reflect the fuel cell efficiency. So we try to use that DC power as such for various applications. So we have demonstrated that the DC appliances, especially DC fans, converters, air conditioner, DC motors, two-wheelers motors, and refrigerator, all are 48 volt DC. So we don't want to convert the DC power into again AC. So we try to demonstrate 48 volt output from the fuel cell. So that is being used for all the essential appliances. So that's all about the stationary application. As I said, we develop a system, and wherever hydrogen is available, we will go and put it our system for the field trials. So that is the current activities going on in a big way. So we demonstrated our system for the Naval Lignite Corporation, where they have a plenty of hydrogen, which is being used for other applications. And Gas Authority of India Limited, so they are having hydrogen. They want to make use of the hydrogen to power their premises. We demonstrate up to 5 kilowatt capacity in these two organizations, and we also built the system for the stationary applications, and we have installed our system at the BARC, where there is hydrogen is available. So as I said, wherever the hydrogen gas is available, the fuel cells, we will go and put it there, and we will do the field trial and get their feedback and how it actually functioning in the actual real conditions apart from the lab actually. So these are some of our demonstrations. Recently, we did demonstration for the disaster management in Tamil Nadu government, because it's in some of the worst conditions in Tamil Nadu government want to use the disaster management. So if you have hydrogen cylinders, and it's a kind of truck where we will have all our PMFC system, and we did demonstration for the emergency power applications, and that was being acknowledged by the Radhakrishnan's current health secretary. And so these are the coming to the stationary applications. So coming to the transport application, so PM fuel cell is playing a major role. So what we did is that it's not a completely fuel cell powered vehicles. We use fuel cell as a range extender with a battery. So we did demonstrations for the Reva car and Go-Kart and Mahindra 3 kilowatt hybrid fuel cell 3-wheelers and 5 kilowatt hybrid fuel cell 3-wheelers and fuel cell powered scooters. So in all the system has our own PM fuel cell stack as a range extender in addition with a battery. So it has all the safety features. So because we are handling hydrogen gas, so ultimately we need to have all the safety alarms and all those things and power converters. And in all this vehicle, we use a very compact, hydrogen cylinders, not very compact, the commercially available hydrogen cylinders, which we carry along with the vehicles. So I will come to that discussion later point of my presentations. Actually, the hydrogen storage, which is most critical steps in if you want to use this PM fuel cell technology for the transport applications actually. So apart from the transport, the forklift actually, which is one of the market area where we can push our PM fuel cell technology in order to power the forklift. So in the warehouse, you can find especially the Amazon, all those international key players. So they have a very big warehouse where they are having many number of forklifts which are being powered by battery or diesel. So they try to replace that battery and other engine powered forklift with the fuel cells. So with that objective, we also develop a air cooled PM fuel cell stack for the forklift applications. Recently we did a demonstration at IOCL. Using forklift fuel cell powered forklift, where the hydrogen storage cylinders is being used as the hydrogen resource, and we do demonstration and display our PMFC system in various expos which are took place in recent years. So some of them have highlighted here. So in globally, if you see in that aspect, the current initiative towards the PM fuel cell transport application, already the Hyundai and Toyota, Honda Clarity, these are all commercially available fuel cell vehicles. So if you see the power capacity of the fuel cells ranging from 100 to 120 kilowatts. So I have also experienced when I visited the Canada, the Toyota Mirai, so which is very quiet, compact and fuel cell powered Toyota Mirai. So as I said, if you want to make such kind of product in developing country like India, we need to go a long way. the main thing is that hydrogen storage actually. So, and the compact fuel cell, because the space the space occupying the system, it should be very compact, and the component, the subcomponents power consumption as well as the space constraints has to be taken care, and obviously the hydrogen storage. So the hydrogen cylinders. So because the hydrogen is a very light gas, if you want to develop a 500 kilometers range uh, passenger vehicle, so the amount of hydrogen requirement is huge. Say for example, 1 kg of hydrogen, if we have about 30 to 40 kilometers, we have a range actually. So if you want to 500 kilometers, if you want to develop a 500 kilometers range passenger vehicles, obviously the amount of hydrogen which we need to carry in the vehicle is huge, because it's a lighter gas. So you need to compress the hydrogen gas at elevated pressure. So that is the main bottleneck actually. So in a developing country like India, we don't have a permission to compress the hydrogen more than 150 bar. So if the commercially available hydrogen cylinders are 150 bar, which is having about 6 kg of hydrogen, 6 meter cube of hydrogen. 6 meter cube of it's not more than, it's equivalent to 0.5 kg of hydrogen. So 0.1 cylinders will take care about not more than 20 kilometer range. So if you see, if you want to develop a system, develop a fuel cell based vehicles of 500 kilometer range, the amount of hydrogen will be about 0.5 kg. I mean, 1 kg is 25 kilometers, approximately 25 to 30 kilometers. So if you want to develop a 500, so the amount of hydrogen is huge. In terms of 10 to 15 kg of hydrogen you need to carry. So that is the thing. So what we have to do is that we need to develop a high pressure cylinders, because hydrogen has the tendency, if you use the metal based cylinders, because the commercially available hydrogen cylinders are 150 bar, it's a steel based. So if you want to handle high pressure cylinders, you need to have a very composite cylinders. So it should avoid hydrogen embrittlement, because if you cannot use metal based, steel based cylinders, because the hydrogen embrittlement will take place, which leads to at high pressure, that hydrogen embrittlement, hydrogen permeation through the metal is high, so that leads to explosion. So we cannot use the steel based cylinders when you want to handle high pressure hydrogen. So the storage of hydrogen, it should be more than 600 bar or 500 bar, at least 300 bar. It should be more than 300 bar storage pressure. So if you want to store that much amount of hydrogen at elevated pressure, you need to have a very compact composite cylinders, which are not available in our country. So the composite cylinders are essential if you want to handle high pressure hydrogen. These are the very key component for the fuel cell electric vehicle when compared with battery based electric vehicles. Only the fuel cell stack, which is the core component of this electric vehicle, and the electric traction motor. This motor drives the vehicle's wheel, and suggest the DC-DC converters, because fuel cell will produce a variable DC. In order to get the constant DC, you must have a proper DC-DC converter, which will also taking care of the input voltage from the battery. And thermal system, the cooling is essential. So like our IC engine, the radiator, and so we need to have an effective cooling system. Say for example, 100 kilowatt fuel cells. These vehicles is having about 100 kilowatt fuel cell. So it also emit 100 kilowatt thermal power. So that has to be dissipated properly. So you need to have a proper thermal system, cooling system, and you must have a battery as auxiliary power, because in an electric drive vehicle, the auxiliary battery provides electricity to the start of the car before the traction battery is engaged, and also power vehicle accessories. So you need to have an auxiliary battery, because for the initial startup, you need to have a battery. So that is called the auxiliary battery system. So that is essential, and which will also take care of the power consumption for the auxiliary equipment. And fuel tank, which are also very crucial in hydrogen based fuel cell vehicle. You need to have a high pressure cylinders. The high pressure in the sense it should be more than 400 to 500 bar pressure. So because if you increase the pressure, the you can reduce the number of cylinders which we need to carry in the vehicles. So that will reduce the vehicle weight and extend the mileage. So that is the concept lying behind that. So you need to use high pressure cylinders, and you must have a fuel filler, because the dispensing stations, because so may have a, you need to have some kind of nozzle which will balance the inlet pressure and the storage pressure. So you must have a fuel filler, so that the nozzle is a very crucial steps which we need to develop in order to operate high pressure hydrogen. And the battery stores energy generated from, because while applying a regenerative braking system, this battery pack will get the power from the, while you are applying the brake and all those things, and it will take care of the supplemental power to the electrical traction motor. So these are the very key components in fuel cell electric vehicles. And when compared with the electric vehicles of lithium battery based electric vehicles, what is the advantage when you go with a fuel cell electric vehicle is that the amount of weight is less, and it takes up less space on the vehicles. When compared with battery pack, the fuel cell stack will not occupy much space, and it generate less greenhouse gases, because so if you want to power the battery, you have to depend on the grid. So in order to get the grid power, you have to burn the natural gas, say for example. So if you take natural gas as the source for hydrogen, as well as natural gas is the source for getting grid power. So in that context, the amount of greenhouse gas emissions when you use hydrogen powered fuel cell electric vehicle is 1.5 to 2.2 times more energy efficient than the battery based. Okay, because so if you use the natural gas as the source for the hydrogen as well as the grid power, so if you see that the amount of natural gas requirement to run the 450 kilometers mileage, so it's about, so the amount of power, the amount of natural gas consumption which is low in the case of hydrogen powered fuel cell electric vehicle when compared with battery based electric vehicle, and it takes less time, to refuel the when compared with battery vehicles. So when you compare price range and time to refuel, the hydrogen fuel cell vehicles, the price ranging from 50 to 60 lakhs, and the range is about 320 to 405 kilometers, and the time is refueling is very less when compared with battery lithium ion battery. It takes about 30 minutes to 12 hours depending on the charging system. And the case of when compared with vehicles, hello. So, in the case of petrol diesel vehicles, though the cost is very less and the range it can be extended up to 650 kilometers, and the time to refuel is similar to the hydrogen fuel based vehicles. So when compared with battery, it occupies less space, less greenhouse gas emissions, and less time for refueling. So these are the main advantage when we go with hydrogen based fuel cell vehicle and compare with lithium ion based electric vehicles. And the challenges towards the development of fuel cell electric vehicle is that the onboard hydrogen storage, as I said, we need to carry less number of hydrogen cylinders. So if you want to carry less number of hydrogen cylinders, you need to have a high pressure storage cylinders. So that is one of the challenges which we are facing. And the cost, because the price, the difference between price and cost, it depends on the margin. So it's a new technology, so the margin has to be less. Obviously that will reflect the price. So the price will go lower when you increase the demand. So that kind of logical policy changes has to be taken care. and durability and reliability, because in the case of transport application, the fuel cell powered vehicle at least has to meet about 5,000 hours lifetime. So that was the target fixed by the Department of Energy for the transport applications, and the cost and reliability, because the fuel cell, the life of the fuel cell has to be at least meet out by 5,000 hours. And hydrogen infrastructure is another challenges, because we need to have a very good infrastructure for refueling the fuel cell vehicles. So fuel cell vehicles are, we can get it, but where is the hydrogen sources, where is the hydrogen infrastructure? So which we need to give a lot of attention for the generation of hydrogen process, as well as creating the infrastructure like our petrol plant. And safety, because as I said, in safety aspect, it's a very lighter gas and it's inflammable. I mean, the flammability of the hydrogen gas lies between 4 to 75%. The 100% hydrogen is completely safe. Only the 4 to 75 is the flammable limit of the hydrogen. So that has to be taken care in terms of safety and public acceptance. So we have to create a lot of awareness among the publics to handle such kind of hydrogen for the electric vehicles. So there is a kind of small analysis when compared with battery and hydrogen. So as I said, hydrogen is not available as such. You have to create from some other source like hydrocarbon or water. So when you still depends on the hydrocarbon, we are also emitting some kind of greenhouse gas. So if you depend completely on renewable based energy system and water as the source for hydrogen, then this route will completely green. So if you take electrolysis of water, because you're getting power from the PV and split the water molecule into hydrogen and oxygen, using that hydrogen and oxygen, use it in fuel cell, you'll get back the power and water. It's a kind of similar to lithium batteries, like charging and discharging. So it's called round trip efficiency. So you're getting, using renewable energy, getting hydrogen, and that hydrogen is, if it use is in fuel cell, you will get back power and water. So if you compare with lithium and battery, so there is a term energy stored on invested. So if you want to develop a 1 kilowatt battery, how much amount of energy which you have spent? So that ratio, and if you use that 1 kilowatt battery for over a period of time, amount of electricity which is generated, amount of energy which is generated from the battery. So if you compare that energy stored on investment, how much amount of energy which you spend to create the battery, and how much of amount of energy which you are getting back from the battery over life period. So if you do that kind of a ratio analysis, the energy stored on invested is, in the case of hydrogen, is more than the lithium ion battery. In the case of ESOA for hydrogen fuel cell is about 59. In the case of lithium battery is about 35, because the amount of energy which we need to create a fuel cell is less when compared with the amount of energy which we need to create the battery. But when you take battery, the round trip efficiency is higher. It's about 82%, because the charging and discharging has high efficiency. Whereas in the case of electrolysis and fuel cell, because we are giving potential of 1.5 volt to split the water molecule, but using that hydrogen in fuel cell, you are operating at 0.6 volt. So you are giving 1.5 volt as the energy input, voltage input, and you are getting 0.6 as the output through fuel cell. So if you try to minimize that gap, 1.5 to 0.6, that will increase the efficiency. Right now, it is about 1.5 to 1.8 volt, which we need to spend for generation of hydrogen. Using that hydrogen, we get back to 0.6 to 0.7 volt in fuel cell. So that gap, if you try to minimize, increase the efficiency, the current 30% efficiency can go up to 50% or near to 45 to 50%. So there is a lot of R&D and material developments, the component development. If we give attention on minimizing the gap of existing between 1.8 to 0.6, so in longer term, the hydrogen fuel cell based electric vehicle will be the ultimate solution for the electric vehicles. With that note, so what need to be done is that the material development. So there are many R&D groups are functioning in India, so only on the material development, not on the system development. So though people like us working on system development, we need to try to consider manufacturing R&D of repeat components. So currently ARCI is developing a fully automated PMFC assembly line. So that will be ready in couple of, maybe ready in next years. So we are going to have a 100 kilowatt per year production capacity of PM fuel cell system. So currently, which we are working on towards that direction, establishing a complete automation line for making a fuel cell stack, and various field trial which we need to attempt, and handling high pressure cylinders in India. So the policy has to be changes. So we are waiting for the government approval to handle high pressure cylinders, especially for the transport applications. And we need to create a set of protocols to handle these hydrogen based fuel cell electric vehicles. So globally there are many protocols are available. So we need to have our own testing protocols and using protocols. So when you want to use the hydrogen based electric vehicles. So, and ultimately the public awareness has to be increased if you want to really take up this technology for the transport applications. So with that objective, the National Hydrogen Fuel Cell Day, because 1.008 is the atomic weight of the hydrogen. So 8th October every year is being celebrated as the National Hydrogen Fuel Cell Day. And last 2 years we also celebrating that National Hydrogen Fuel Cell Day in our by conducting various workshops and demonstrations. And last 2 years we conducted, and this year tomorrow we are conducting on virtual platform of celebrating the Hydrogen Fuel Cell Day to create the awareness among the public by conducting series of eminent lectures and conducting some demonstrations for the public awareness. And as I said, we need to live with the carbon. So currently we are living with more carbon. In future, we need to live with less carbon with more hydrogen. With that end note, thank for the opportunity, and I am open to your questions. Thank you.